Welcome back to the deep dive. Our mission today is pretty focused. We've got this stack of really detailed technical sources covering the JN0-351 certification material. Now, before you think this is just exam prep, let's be clear. This material, these practice questions, they're actually a great way to get right to the operational core of Junos OS. We want to pull out the key stuff, how the network shares info, how it handles failures, those default settings that matter.
Right, that's the goal here. Turn prep into practical knowledge. I mean, the sources say, yeah, it's 65 multiple choice questions, 90 minutes, Junos 23.1, standard exam stuff. But what we want is to extract those core operational facts, the things you actually need to know when, things go wrong at 3 a.m. We're aiming for those little aha moments.
Okay, let's dive in then. Section 1, controlling the flow. Routing. How does a device decide what to tell its neighbors? That takes us right to export routing policy.
Yeah, and this is a really common point of confusion. You've got import and export policies, right? Import is about what routes you accept from others and put in your own table.
And export. That's the opposite, what goes out.
Exactly. It's the gatekeeper for outgoing advertisements. It has zero effect on your local routing table. Export policy looks at rights already in your table and decides which ones you're allowed to advertise to a neighbor.
Okay, so it filters what you share.
Precisely. Think about it. You might have 1,000 routes locally, but maybe for security or just topology control, you only want to share 10 specific ones with a certain peer. That's where the export policy comes in. You set up terms, match the routes, and apply an action, accept or reject, before the update even leaves your router. Purely outbound control.
Got it. And that makes me think about scale. If you're controlling what you share, you probably also need to manage how much you share. Route aggregation, right?
Absolutely crucial for scale. As networks get bigger, the sheer number of individual routes, those prefixes, it can just explode. He slows down routers, eats up memory everywhere.
So aggregation tidies that up. It's the elegant fix. You take a whole bunch of specific routes, could be hundreds, maybe thousands, and you summarize them. Represent them with just one single, broader advertisement.
And why is that so important operationally? For someone listening, why care?
Because the benefit is huge. If you turn, say, 500 specific routes into just one summary route, you're not just shrinking that one advertisement.
Right.
You're drastically cutting down the size of routing tables on all your neighboring routers. Everything gets faster. Convergence speeds up. Updates are quicker. It's fundamental for a scalable network.
Okay, that makes sense. Let's switch gears a bit from layer 3 scaling down to layer 2 and into section 2. Ensuring network stability. How do we keep the topology stable and handle failures? Starting with Rapid Spanning Tree Protocol, RSTP, on switches like the EX series.
Yeah, layer 2 stability is all about preventing loops, obviously, but you still need traffic to flow. And RSTP, well, the sources highlight a really critical point. Only certain port roles actually forward user traffic.
Okay, and which two roles are those? The ones carrying the data?
Those are the root port and the designated port. Simple as that.
Explain those quickly. Root port.
Root port is the switch's single best path towards the root bridge. Think upstream.
Okay. And designated.
Designated port forwards traffic downstream onto a network segment. That's how users connect.
So it's crucial to contrast those with the others then, alternate and backup ports.
Right. Those are deliberately not forwarding. They're in a blocking or discarding state. That's the loop prevention part of spanning tree.
So if your port isn't root or designated, it's actively blocking traffic. That's the guarantee.
Oh, that's the operational guarantee of RSTP, exactly. Keeps the layer 2 world stable.
Okay, jumping back up to layer 3 stability. OSPF, open shortest path first. Specifically, the designated router election. The DR, how does that work?
The DR election. People often get this wrong. They think it's just about the highest router ID.
But it's not.
No, the sources are very clear. The number one criteria is the configured OSPF router priority.
Yeah.
Highest priority value wins. That router becomes the DR.
Priority first. So the router ID is just a tiebreaker.
Exactly. Only if priorities are equal does the highest router ID decide the winner. Priority trumps ID.
Interesting. And remind us why OSPF even does this election. On broadcast networks or NBMA?
Oh, it's purely for efficiency and stability. Imagine if every router had to form an adjacency, a full connection with every single other router on that segment.
Right, that would get messy fast. N-squared problem.
Totally unscalable. So the DR and the backup DR, the BDR, act as central points. Everyone talks to the DR and BDR. They manage the adjacencies. They handle flooding the updates, the LSAs. Much less chatter, much more stable.
Okay, now for something really critical for resilience. Handling failure of the main control plane, the routing engine itself. Graceful routing engine switchover. GRES.
Yes, GRES. This is like the holy grail for high availability, right? The idea is the backup routing engine takes over seamlessly if the primary fails. No drop packets, no lost sessions.
But it's not automatic. There are conditions. The sources mentioned 2 essential requirements.
Absolutely essential. And one is a real operational gotcha. If you miss it, GRES just won't work smoothly.
Okay, let's hit the gotcha first. What trips people up?
Software versions. Both routing engines, the primary and the backup, they must be running the exact same Junos OS software version. Not just close, identical, down to the maintenance release.
Wait, why so strict? Can it handle slight differences?
You'd think so, but no. GRES relies on the backup having a perfect mirror of the primary state. Kernel state, interface state, everything. If the underlying OS versions don't match perfectly, that synchronized state can't be trusted. The backup might not understand something the primary was doing, so the switchover fails, or it's messy. You could end up with a full reboot, major outage, not graceful at all.
Okay, identical software versions. Critical.
Yeah.
And the second requirement, it relates to that state you mentioned.
Yes, the state synchronization itself. It needs to be active and fully complete before any switchover happens. The backup RE has to be constantly receiving updates from the primary, keeping its copy of the kernel and interface state perfectly in sync in real time.
So identical software, complete, ongoing state sync. Those two together make seamless failover possible.
That's the foundation of GRES.
All right, let's shift gears into Section 3. We're looking at how the network handles traffic more granularly, security, quality of service, even internal connections. Starting at Layer 2 again with DHCP snooping.
Right, DHCP snooping. It's a basic but really effective security feature, mainly to stop IP address spoofing at the network edge.
How does it do that? It builds some kind of table, right?
Yeah, it builds a dynamic binding table. It basically watches the DHCP conversations, the requests, and the offers, and it records who got what IP address. It creates a trusted list.
Okay, so what specific information does it have to store in that table to be useful against spoofing? The sources mentioned 3 things.
3 key pieces. The client's MSE address, the IP address that the DHCP server officially assigned to that MSE, and this is crucial, the specific switch interface that client is plugged into.
MSE, IP, and interface. Why all 3?
Because that combination lets the switch validate traffic. If a packet comes in on, say, interface 005 claiming to be from IP 192.168.11100, the switch checks its snooping database. Does the entry for 192.168.110 list interface 005 and the correct source MC address from the packet? If not, maybe the MSE is wrong or that IP should be on a different port. The switch knows something's fishy, likely spoofing.
And it drops the packet.
Drops it. Simple, effective access layer security.
Okay, moving up the stack a bit. Quality of service, or class of service, COS in Junos terms. The key difference between what happens when traffic comes in versus when it goes out. Classifiers versus rewrite rules.
Exactly. The timing and location are everything here. Classifiers first.
Where do they operate?
Strictly on ingress. As a packet enters the Junos device, the classifier looks at the packet maybe at its existing DSCP marking or VLAN tag priority. And based on configured rules, it assigns that packet an internal forwarding class, like best effort, expedited forwarding, whatever, and a lost priority. This decides how the packet is treated inside the router or switch.
So classification happens on the way in, setting internal treatment. What about rewrite rules then?
Rewrite rules are the opposite. They happen on egress just before the packet leaves an interface.
And their job is?
Their job is often to change the packet's marking, like modifying the DSCP value in the IP header.
But why change it on the way out? Didn't we already classify it?
You did for internal handling. But the outside world, the next network maybe, might have different requirements or trust levels. Maybe you classified some internal traffic as high priority, but your agreement with the next provider says you can only mark it with a specific, perhaps lower DSCP value.
Ah, so rewrite rules enforce the policy for the next hop.
Exactly. Ingress classifies for internal treatment. Egress rewrites ensure you meet the external requirements or policy for the traffic you're sending out.
Got it. Now, something a bit more niche, but interesting for internal plumbing. Logical tunnel interfaces, LT interfaces.
Yeah, LT interfaces are neat. They're virtual, point-to-point links, but their specific purpose is pretty unique.
Which is?
They connect 2 different routing instances, think VRFs, but on the same physical device.
Oh, okay. So instead of needing a physical cable looping back from one port to another to connect 2 VRFs on the same box.
Right. You use an LT interface. Saves physical ports, simplifies cabling. You basically configure it by linking 2 logical unit numbers together, like ELT0000.0 and ELT0000.1, they become the two ends of this virtual wire inside the chassis.
Clever way to link internal virtual networks. Okay, let's hit a really critical security point now. Firewall filters in Junos. Specifically, the default behavior if you don't finish your filter properly.
This is absolutely fundamental. If you configure a firewall filter, apply it to an interface, but you forget to put an explicit final term, usually a then accept or then discard, that catches everything else.
What happens? Does it just allow everything that didn't match?
No, quite the opposite, thankfully. Junos performs two actions by default, implicitly.
Okay, action 1.
Action 1. It adds an invisible final term at the very end of your filter that says then discard. It's a default deny, safety net. Any packet that flowed through all your terms without matching anything gets dropped.
Okay, that's good for security. Prevents accidental leaks. What's action 2? You said there were 2 things.
Action 2 is the one that causes troubleshooting headaches. The discard is silent.
Silent, meaning?
Meaning it doesn't log the discarded packets, it doesn't increment any counters you can easily see for that implicit drop. The packets just vanish. Poof.
So it protects the network but leaves you blind if traffic is unexpectedly disappearing because it hit that implicit rule.
Exactly. Pure security mechanism, but terrible for visibility if you're not aware it's happening.
Which really underlines the importance of explicit configuration. Okay, one last quick one from the sources tying everything together. Time synchronization.
Yeah, a simple utility, but essential. All those logs, event correlations, security mechanisms we talked about, they depend on accurate, synchronized time across all devices.
And the standard way to achieve that?
Network Time Protocol, NTP. It's the bedrock utility ensuring every router, switch, firewall, and server agrees on what time it is. Without it, troubleshooting across multiple devices becomes almost impossible. Your logs won't line up. Building on what we just discussed, think about that implicit silent discard rule in Junos firewall filters. We know it's there.
Yeah.
So why is it considered an absolute best practice essential, really, for network operators to always add an explicit final term, like then discard log or then reject count, even though the implicit discard already drops the packets? What's the real operational cost of that silence when you're trying to figure out why something isn't working?
That's a great question to ponder. What's the hidden cost of not seeing what's being dropped? Something to think about as you work with these systems. We hope digging into these details helps you on your journey. Thanks for joining our deep dive today.